So now we're going to take a look at experimental design. Now, experimental design is the most important part of statistics. The reason why it's the most important part of statistics is that over the last 2 years we've looked at lots of different hypothesis tests and analysis of data, but experimental design looks at how that data has been collected and the measures that have been put in place while collecting it. And the reason why this is so important is that if the data isn't collected properly or effectively enough, then the hypothesis test or the analysis that we perform on the data is completely useless. It isn't telling us anything that is going to be statistically significant, and that is when people start disputing the findings of tests. So it's very important. Unfortunately, it is quite a dry topic. It's going to be a lot of me talking, so I apologise in advance for that. So we're going to start off experimental design by having a look at experimental error. So experimental error happens when you perform the same experiment multiple times by obtaining different results. This does not necessarily mean that a mistake has been made, but the experiment's results have been affected by other factors. Quite often, if you take more than one sample from the same population, you will be finding different results, but we're talking about here finding results that are completely different in the fact that it's not what we were testing that's been affecting it. So quite a lot of times we talked about, when we had a look at confidence intervals, we talked about how the mean from a sample, we'd expect it to be in a certain range, depending on if we found a 90% confidence interval or 95% confidence interval, then we'd expect the means of other samples to lie within that confidence interval. We're talking about it being outside of that, and the reason for that being is that other factors have affected the outcome. So experimental error should be minimised as much as possible by keeping factors which are not being investigated as consistent as possible by careful experimental design. It is desirable to take repeat observations or replicates under apparently identical conditions in order to estimate the experimental error. So not just getting a sample once, but taking a sample multiple times to check for the variation in the results. One of the best ways and most often ways to reduce experimental error is to plan with paired comparisons. So experimental error is the effect of factors other than the controlled by the experimenter. So if we're trying to test for if the bottling machine has increased or decreased the amount of volume of liquid being produced or dispensed into a bottle, then we want to make sure that any difference that we have found is due to the new machine, not any other variables. So when we're setting up our experiment, experimental design is important to ensure relevant and valid conclusions can be drawn from the experiments and try to extract a lot of information from a relatively small amount of experimentation. Statistics are often asked to produce statisticians, that should say, are often asked to produce summary statistics from large, haphazardly collected data. This is called exploratory data analysis. The term data mining is also applied to exploring huge sets of data. And quite often, if you get a job in data analysis, this is the type of data that you will be using. You'll be using data that's collected through Google searches or things that have come up on Facebook, and then you'll be using that data to tailor make ads for that customer that they are more likely to use. And this is actually what quite a lot of systems use. And the reason why it's haphazardly collected is that you get random bits of data associated to random people. And also some of the data may be missing, some of it may be outliers, and you have to take all this into account when you're having a look at the data and when you're exploring it. So exploratory data analysis or data mining is where we're having a look at a large, haphazardly collected sets of data. So by contrast, designed experiments data is collected in an exact specified manner, and the purpose and method of analysis is known before the experiment is undertaken. In particular ideal situations, it's not always achievable. So most of the questions that we get in our statistics exam are going to have a designed experiment behind them. And the reason for that being is that we need to have a specific way that we're wanting to analyse it. Sometimes you might be given a large set of data and asked to explore the data, and that's more of a data mining experience, but it's not as large. When we're talking about large sets of data for the data mining and the exploratory data analysis, we're talking about thousands and thousands of pieces of data that we're having to look through and make connections from, which obviously they can't give you in an exam. So most of the stuff that we're looking at is going to be designed experiments, and most of the stuff that you might have practiced in lessons is also going to be designed experiments where we knew what we were going to look at and then we collected the data, instead of being given a large set of data and then being told to just analyse it. So experimental design is used to eliminate bias, reduce experimental error in data collection. Quite often what we find though is that because we're designing experiments, we need to be careful, because we already know what we're wanting to test before we collect the data, that this doesn't sway the way that we collect the data or the items that we include in our analysis. Because quite often what you might find, if the experiment isn't designed properly, some values are automatically written out without further exploration of why the data gave that value, which then actually reduces the validity of the results. Because if that was an actual result and had no, for instance, human error entering it into the computer or something like that, then it would have been better to explore why that value came out as it was, not just ignore the fact that it existed. So we're going to highlight in this example the areas in the following situation where the experiment has been designed to reduce experimental error. So we have the fuel consumption of a car is measured 20 times. Ted drives the car each time along a predetermined route at the same time of day. Before planning which day to perform the experiment on, Ted watches the weather forecast to make sure that the weather will be sunny each day. Ted always begins his route by filling up the car at the same petrol station using the same amount and type of fuel. So, straight away, the fuel consumption of a car is measured 20 times. So, by this telling us that they're doing it 20 times, we have replicates. So, we're repeating the experiment 20 times. Also, we have Ted drives the car each time. So we are controlling the driver along a predetermined route. So same route, and also at the same time of day. Now this is important because obviously the amount of traffic that's on the road varies from time to time during the day. So before planning which days to perform the experiment on, Ted watched the weather forecast to make sure that the weather will be sunny on each day. So again, the weather is another thing that we are controlling. And again, if it's raining, people tend to move slower, more cautiously. So Ted always begins the route by filling up his car. So we always fill up the car with the same at the same petrol station with the same amount and type of fuel. So we always fill the car at the same station, same amount of fuel, and the same type of fuel. Now, the reason for these last two is that the amount of fuel that we have in the car will make the car heavier or lighter, depending on if you have more or less fuel in it. And that in turn will affect the amount of fuel that's being consumed, as well as having the same amount of fuel just to start off with. But also the same type of fuel, so the same fuel type. The same type of fuel is because you have more high-performing fuels, which usually have less impurities, and therefore make your car run better for longer. And this may be the reason for the difference in the values. So there's quite a lot there that Ted controlled, quite a lot that he tried to make the same. So I think that if he actually performed that experiment, he would get some good results. So I'd now like you to try the now you try question, again highlighting where the experimental error has been tried to be reduced through the experimental design. But also I want you to highlight areas in the now you try question where you think that it should have been controlled better or differently in order to reduce the experimental error more. So hopefully you paused the video and you gave the now you try question a go. So we've got a greengrocer normally obtains her fruit and vegetables from a market in Manchester. She wishes to find out whether obtaining her supplies from a different market in Preston would increase her daily takings. The greengrocer identifies 8 clear days in which she sells the produce from Manchester and 8 cloudy days to sell the produce purchased from Preston market. Each of the 16 days is chosen when there are no events on in the local area. So the things that the greengrocer has controlled is that they've got the same number of replicates for Manchester and Preston. We're repeating the experiment. We've not just got 1 day for each. We've got 8 days for Manchester and 8 days for Preston. And also on all of these days, they've made sure that there's no local events on so that it's likely that the same amount of people will come. However, as you can see highlighted in pink here, they've chosen 2 different types of weather. So it's always going to be clear when they're selling the Manchester stuff, and it's always going to be cloudy when they're selling the Preston stuff. So we wouldn't know if it was the fact that it was from the Manchester or the fact that it was from Preston that was affecting the difference in sales, or the change in weather. So my first suggestion is to have the same weather for when you're selling them from Manchester and from Preston. Also have the same days, because quite a lot of times people are more likely to go shopping at the weekend instead of during the week, because people work during the week usually. Making sure it's not any bank holidays or anything like that. So certain things like that, having it so that it's the same day. But also, it just says about fruit and veg. It doesn't say that she's got the same types of fruit and veg available or the same amount of fruits and veg available from each of the markets. So if she bought like a really good wide selection from Manchester and then a couple of apples and bananas from Preston, again, we wouldn't know if it was the range that she was offering or where she got it from that was affecting the sales. So this experiment, I would say, at the minute, it's not very well designed, needs a lot more effort being put into it to be able to control those variables. Better experimental design to reduce the experimental error. So carrying on looking at experimental design, we're now going to have a look at paired comparison. So in a paired comparison, experimental error is reduced by applying both treatments to the same subject in the same conditions or similar subjects in the same conditions. Now, if you study anything like psychology, this comes up all the time in psychology. Twins are used for all types of experiments, and the reason for that is that those erroneous variables are being controlled through the fact that they are twins. They grew up, they have very similar genetics, they have the same nurture, they have the same nature, and it's only the variable that they're wanting to experiment on which is being changed. So twins are used quite a lot. So here we have twins are very good for paired experiments to reduce experimental error, as the erroneous affecting factors are already being replicated in the subject's twin partner. If two experimental factors are varying during an experiment so that we cannot identify if it is a change in these experimental factors that altered the result, so the dependent or the response variable, or if it was the explanatory or independent variable, the external factor is said to be confounded. So for instance, if we were trying to measure IQ, our dependent variable, on, let's say, how much broccoli they ate the week before, which would be our explanatory or independent variable, but actually it also turned out that one of the other participants ate a lot of chocolate, then we might, or drank a lot of coffee, we might find that that is a confounded variable. If it's not only broccoli that is the changing diet that they have, then it might be the other factors that are confounded our results. Now, also, having paired experiments is quite important, because if we were designing an experiment where we wanted to see how different drugs worked, and we had a control group and experimental group, and we had the same person in both of those groups, and let's say that we were having a look at reaction times, maybe it's the fact that they already knew how the experiment was going to run that changed their reaction time in whichever one of those situations they were in second, rather than the fact that they were in the control group or the experimental group at this time. So having paired data, even if it's not twins, is sometimes better than having the same person do the same activity before and after something has happened, because you don't know if it's the fact that they've completed the maze twice, or they've done the experiment twice, or whatever it is that you're trying to test, and that's why they've got better at it. So the greengrocer in example 2 can improve her experiment by altering which days she sold produce on the market from Manchester and Preston, in which case the final decision would be which produce to sell in the first week. As there is no obvious reason as to why one way would be preferred over the other way, the choice should be randomly processed, such as tossing a coin. This is known as randomization and helps to prevent unconscious and unsuspected bias. So this is where we have, let's say, twins, we have a control group, we have an experimental group. There should be no reason why one of the twins should perform better in the control group or the experimental group, so they should be put into these groups randomly. Similarly, if you have paired data where they're not twins, again, if you're pairing them together so that all the erroneous factors are being taken into consideration when you're pairing them together, there should be no reason why one should be put in the control and one in the experimental. This is also quite important when we're talking about giving people a placebo and giving people a drug, because if we're wanting them to be completely honest, then they shouldn't be told you're going to get a placebo the first time, you're going to get a drug the second time. It should just be, we're going to give you something, we're going to see how it's going to affect your asthma or something like that. So in which case it should be randomized who gets the placebo first and who gets the drug first, and not just that everybody gets the placebo first and everyone gets the drug second, because again, it could be the fact that they were given that way round which affected the outcome. So this is also why it is important to randomly select, it's also important that a random sample is collected before performing an analysis on data to ensure that the sample is selected has not been influenced by bias. This is because a random sample is defined as a random of selected size being taken from a population in a way that all possible samples and sizes of sample have an equal chance of being selected. So this is very important. We have to give everybody an equal chance of being selected. We can't have one person being preferred to be chosen over another. We need it to be a random sample. And if you have a look back at the sampling section from last year, we talked about the fact that actually there's only two different types of random samples, which is the simple random sample and the unrestricted random sample. And the only difference between them is whether we include replicates or not. Usually in these experiments, we're talking about a simple random sample. The reason being is that we don't want to include the same person in the experiment twice, because again, we're giving that person more control over the outcome. So the purpose of randomization is to eliminate bias, and we're going to talk about that a little bit more in the coming sections in our experimental design. So again, we've got an example. So we've got the mean payment made by an insurance company on household claims in 2000 was £632. The manager now examined 180 randomly selected claims made in 2001. She found that the mean payment is £768 with a standard deviation of £299. Assuming that the size of the payments may be modelled using the normal distribution, use the results from the 180 claims to investigate at 1% significance level whether the mean payment has increased since 2001 compared to 2002. So here we have a single sample of data, so that is our data from 2001 that we are experimenting on. And we have a large sample size, we have a mean and a standard deviation that we are talking about, so that means that this is going to be a normal hypothesis test. So it doesn't matter that we've only got the sample standard deviation because our sample size is sufficiently large. So our H0 is going to be that the mean is still 632. H1 we're looking for an increase, so we're seeing that the mean is more than 632. Then we need to find the mean of our sample. Well, we've already been told that. That's 768. And remember that our new standard deviation is going to be the same as the old standard deviation, or in this case the sample standard deviation, divided by the square root of the sample size due to central limit theorem. So because 768 is bigger than 632, or because we've got a one-tailed test where our inequality symbol is pointing this way, we're going to be looking at the probability that x is greater than or equal to 768. So then we're going to stat, dist, norm, NCD. Our lower is going to be 768. Our upper is going to be a really big positive number. Our standard deviation is 299 divided by the square root, 299 divided by the square root of the sample size, which is 180, and the mean is 632. So that gives us 0.9 zeros there, 522. That is our test statistic. You could keep it in standard form if you wanted to, due to the fact that it is a very small number. 1, 2, 3, 4, 5, 6, 7, 8, 9. Remember, this is standard form here. So for the critical value, It's a one-tail hypothesis test, so it's just going to be the same as the significance level, so 0.01. And then as the test statistic is smaller than the critical value, we're going to reject H0 at a 1% significance level. There is sufficient evidence to suggest the mean claim is more than £632 in 2001. Now, the reason why it's asked this is because then we're going on to having a look at what the population was like. So how would your conclusion be effective if you discovered that the size of the payments was not normally distributed? Well, as our sample is sufficiently large, the means of the samples will be normally distributed regardless of the population distribution and this is due to central limit theorem. So if you are setting up an experiment and you have a population of data and you are uncertain if it is normally distributed, you are better taking a large sample to ensure that if it turned out that the population was not normally distributed, that the results that you have found are still valid. So if the sample is not random, then this means that our results would be invalid, as we may have experimenter bias in our sample selected. So I'd now like you to pause the video and give the Now You Try question a go. So hopefully you paused the video and you gave the Now You Try question a go. So we have the mean number of cakes sold per day in 2017 is 35. A random sample of 25 days from 2018 were selected and the number of cakes sold was recorded. They found that the number of cakes sold was 32 with a standard deviation of 4 cakes per day. Assuming that the number of cakes sold may be modelled by a normal distribution, use the results from the 25 days to investigate at a 1% significance level whether the mean cakes sold decrease from 2017 to 2018. So this time we have a small sample because we only have 25 days and we only have the sample standard deviation, which means that we should use T. So our H0 should be that the mean equals 35. Our H1 should be that the mean is less than 35. And then you can see my summary parts here. This is just from the question that the sample mean is 32, the sample standard deviation is 4, and the number of trials was 25. So then you need to go into test T1 sample. Our symbol in our hypothesis test is the less than inequality sign. We're looking at less than 35. The mean from our sample was 32. The sample standard deviation was 4. And the number of trials was 25. And that gave us a T of minus 3.75. That's our test statistic. So the size of our test statistic is 3.75. Our degrees of freedom, remember that's the number of pieces of data minus 1, which gives us our degrees of freedom as 24. We're using a 1% significance level and it's a one-tailed test, so we should be looking down from 0.99 and across from 24, which gives us a critical value of 2.492. So then as the size of the test statistic, sorry, I missed my modulus lines off there. The size of the test statistic is bigger, than the critical value. Put my inequality symbol wrong there as well. There we go. Reject H0 at a 1% significance level. There is sufficient evidence to suggest that the mean sales of cakes is less than 35 per day. So then again, we're being asked what would happen if it turned out that the size of the payments was not normally distributed. Sorry, that should say the number of cakes sold. And this time, because we have a small sample, this would invalidate our result as the sample is small, it's less than 30. So the population must be normally distributed for the means of the samples to be normally distributed, and this again is due to central limit theorem. What would happen if the sample was not random? Again, this would invalidate our result as we must have a random sample to eliminate that experimental bias. There might be experimental bias in the sample selected. So if we were asked how we would improve the experimental design if we did find out that the population was not normally distributed, then we could just say that we would take a larger sample. So now we're going to move on to talking about blocking factors. So blocking factors is a new idea. We haven't come across it yet before. But we are going to have a look into a whole area of statistical hypothesis testing that opens up when we use blocking factors. So if we think back to our greengrocer example from before, if we decided to test which of the markets was better, and this time we've got even more variation, we've got Kirkham, we've got Manchester, we've got Oldham, we've got Preston, and she has 22 days where she can allocate the 4 locations, so where she gets her produce from. She could use a random process to decide to sell the produce from each market each day, subject to the same market being shown no more than 6 days. And there's a way that she could set this up. So she could, this is just an example, there's loads of different ways that she could set this up. As you can see here, she could do it 5 days from Kirkham, 6 days in Manchester, 5 from Oldham, 6 from Preston. That's the 22 days where she's selling the produce from different places. And this is what we call a completely randomized design. And the way that we would analyse it would be using a one-factor analysis of variance. So this is the design, and we would analyse it using a one-factor analysis of variance. Now, the one factor here that we're having a look at is where she got the produce from. However, if we wanted to improve on this design, then we could add a blocking factor. So a blocking factor is another thing that we are going to control to be able to see if it was where she was getting her produce from, or, for example, here we have added the blocking factor of which day of the week she sells the produce on that was affecting the sales. So once we have added this blocking factor of the days of the week, this is now what we call a randomized block design. And again, this is the experimental design that is being used. The markets are being blocked by the days of the week. And we would analyse this through a 2-factor analysis of variance. So this is our analysis. One of the factors is the market, and the other factor is the day of the week being introduced, because it is thought that to have a subsequent effect on the results. Because maybe, I know that where I grew up, the markets were open Thursdays and Saturdays, so maybe more people are going to go on Thursday, maybe more people are going to go on a Saturday, because they might go to the greengrocers when they're going to the markets. But again, we're thinking that the day of the week is going to be affecting our sales. So this is known as the blocking factor. So the days of the week are our blocking factor. And this is used to reduce experimental error and improve the detection in the experiment. If two blocking factors are introduced, then we have what's called a Latin square, which we analyse using a Latin square design. It's where we have two blocking factors. However, it's unlikely that they're going to get you to do a full Latin square question due to the fact that it takes quite a lot of time. So together we have three forms of analysis, which are the Latin square, the two-factor analysis of variance, and the one-factor analysis of variance. And we have two different types of design, which is the completely randomised design and the randomised block design. So a blocking factor is used to reduce experimental error by applying treatments, usually more than two, to the same subject or in the same conditions. So here we have an example. So in comparison of drying times of three different types of wood preservative, A, B and C, samples of each of four different woods, we have wood 1, wood 2, wood 3, wood 4 are available. And we have three designs set up here. So you can see that we have design 1 where A is being applied to wood 1 3 times, B is being applied to wood 2 3 times, and C we have wood 3 and it's being applied to it. Treatment C is being applied to wood 3 3 times. Then we have design 2 where treatment A is being applied to wood 1, wood 2, wood 3, wood 4 and then wood 1 again. Treatment B is being applied to 2, 3, 1, 4 and then 2 again, and then treatment C is being applied to 1, 3, 2, 4 and 3 again. For design 3, we have that treatment A is being applied to wood 1, 3, 4, 2. B is being applied to 2, 4, 1, 3 and C is being applied to 3, 2, 4, 1. So thus, for example, the first column for design 2 indicates that preservative A is applied to 2 samples of wood 1 and 1 sample of wood 2, 3 and 4. And it tells us that the written order within the columns is unimportant. So it's not necessarily meaning in design 2 that in A it's being applied to 1, then 2, then 3, then 4, then 1. It's just telling us that it's being applied to 2 of the wood 1s and 1 of the 2, 3 and 4. So then we are being asked to state 2 disadvantages of design 1. So remember, design 1 is where A was applied to wood 1 3 times, B to wood 2 3 times and C to wood 3 times. So 2 disadvantages that I can think of is that the same wood is being used multiple times with the same treatment. And each treatment is being applied to a different type of wood. So we're not going to be able to tell if drying times were affected by the treatment used or type of wood. For part B, we're asked to name the design of design 3. So if we have a quick look back at what design 3 looked like. So design 3 was where, if we have a look, considering it tells us that the order that we apply, the order in the list is unimportant, that means that wood 1 has treatment A being applied to it, treatment B being applied to it, and treatment C being applied to it. Wood 2, again, A, B, and C. 3, A, B, and C. And 4 is also being applied, also has treatment A, B, and C being applied to it. So because each wood is being used once and only once, we could change that design so that instead it's set up so that we have treatment A, B, and C, wood 1, wood 2, wood 3, wood 4, and then we could have the drying times, filled in the table here like this. Now this looks similar to one that we've had a look at. So we're trying to name the design. So this is a randomized block design. So then we're trying to name the technique used to analyze design 3. So that would be a 2-factor analysis of variance. So then we're stating one advantage to design 3 over design 2. So if we have a quick look back again, in design 2 we have wood 1 being having treatment A applied twice, B applied once, C applied once. For wood treatment 2, type of wood 2, that's having treatment A applied once, B applied twice, and C applied once. Wood 3 has A applied once and B applied once, but C applied twice. And for wood 4, it just has each of the treatments being applied once. Now the disadvantage to this is that any difference that we find, so any difference is being swayed by the fact some treatments are being applied to the same type of wood more than once in design 2, whereas in design 3 each treatment is only applied to each wood once. And the reason why this is an advantage is because if it turned out that wood 1 meant that the treatment dried faster, then treatment A in design 2 is going to be skewed by that fact, because treatment A was applied to wood 1 twice, whereas treatment B and C were only being applied to wood 1 once, and therefore they're not getting the advantage of that shorter drying time twice like the treatment A is. And similarly, if wood 1 meant that the treatment dried more slowly, then treatment A is at a disadvantage because it's being applied to wood 1 twice. So you have to think very carefully about this when you are working through it. So we're trying to explain how randomization might be used in context of design 1, 2 and 3. Well, we could be using it. We could use randomization to decide the order of which the treatments are applied to the wood. And the reason why it's important that we use randomization for this is that there shouldn't be a set way that's meaning that we are increasing the drying time or decreasing the drying time just because of where it is in the order of being applied to the wood. Now, in reality, if you think about what's happening here, even if this person was just stood in a room on their own and they were applying these treatments to these pieces of wood, because they are in the room, depending on the time of the year as well and the weather, the temperature in that room could be rising because the person is in there, even just small, even just like by a small amount, which could affect the drying time. So that needs to be really clear that they're not going to pick and choose which one to apply first or which wood to apply it to first, because it should be using randomization to decide this in order to make sure that that's not bringing in experimenter bias. So I'd now like you to try the Now You Try question. Very similar again. It does go over onto the next page as well. Please just ignore this E here. That is meant to be a part A, I. So it does go on to this page as well. So please pause the video now and give this Now You Try question a go. So now we're going to go through the Now You Try question. So we've got, if a manufacturer wishes to compare 4 different types of soap, A, B, C and D, and has 12 people available to test them, S1 through S12, then they could randomly allocate each person to a soap given the following design. So don't be caught out here. The soap is A, B, C and D. The people are S1 through 12. So this design is called a completely randomized design because everybody's only testing the soap once, and we would analyse that using a 1-factor analysis of variance. So alternatively, the manufacturer might decide to randomly choose 3 subjects and use them for all 4 soaps given the following design. So again, we have soaps A through D across the top, and then we have S1, S2 and S3 going down the side. So similar to the last question, we could have A, B and C. Sorry about that. A, B, C and D going across the top. Down the side, S1, S2, S3 for the soaps. And we can have whatever values we're trying to find out about them, their rating or whatever it is in the table. So this is then called a randomized block design because the people are our blocking factor. And we would analyse it using a 2-factor analysis of variance. Now, the advantage to using this design over the first design is that we can tell if people are affecting the outcome or if it is actually the type of soap that's affecting the outcome. So then for part C, we've got alternatively, the manufacturer might use the following nameless design where A is being used by person 1 twice and then person 3. So B is being used by person 2 twice and person 6 once. C is being used by 4 twice and 9 once, and D is being used by 5 twice and 12 once. Why is this the worst design than the first two? Well, we've got the same person using the same soap multiple times, and also we have each person only using one type of soap. So person 1 can't make a comparison between soap A and soap B because they're only using that first soap. But also that person is using the same soap twice. So if their result is really good or really bad, that is going to affect the outcome for A. And the same with person 2 for B, and so on. So that is why this is the worst design. So just a little bit more to look at here. It is quite a large section. Again, I apologise for this. So we have, when we are wanting to measure the effect or changing one variable to see how it affects the other, it is usual to have what's called a control group and an experimental group. And we've talked about these before quite a lot. These two groups should match as closely as possible, meaning that the groups as a whole should be very similar, not necessarily that each subject in each member individually has a pair in the other group, but that the groups altogether are very closely matched. Now, if you've had a look at any kind of experimental design before, so again, for example, I know in psychology, I think a little bit in biology as well, you might have talked about a blind study and a double blind study. So a blind study is where the control group is given what's called a placebo to make the patient unaware that they are not getting the experimental treatment. And the reason why they do this is because if the patient who took the placebo knew that they were taking the placebo, then they would know that they would not be getting, for instance, the drug that they needed. And it's essential that the participant does not know that they are taking a placebo, because part of it, why we're doing this, is to eliminate the psychological effect of thinking that you are improving, when in reality it's just that you are thinking that you're improving and therefore you are improving. So in lots and lots of medical research, they'll have a control group which will receive a placebo, but that could be a blind study where the participant does not know that they are on a placebo. There is also a double-blind study, and this is more commonly used, and the reason for that is to, again, eliminate the experimenter bias. So a double-blind study trial, neither the person administering the test or the person or the participant in the study knows that they are receiving a placebo or the actual treatment, and this limits experimenter error through the behaviour of the administrator. Would not sway the knowledge or preconceived notions of how the treatment or placebo should affect the patient. So, for instance, if you were testing a new medicine and you knew that a person was on a placebo and they came to you and they talked about the fact that they were getting really bad headaches, then you might just be like, oh, you'll be all right, don't worry about it. But if you didn't know if they were on the drug or the placebo, then you might treat them better and be more inquisitive about the headaches, what's caused them, the frequency, the severity of them. And that kind of level of care can really affect how the patient feels throughout the trial. So again, we're going to have a look at an example. We've got to measure the effectiveness of a drug to relieve breathlessness. 12 subjects, all susceptible to breathlessness, were each administered the drug after one attack of breathlessness and a placebo after a separate attack. 1 hour after the attack, the index of breathlessness was obtained for each subject with the following results. So we have here subject 1, When they got the drug, their breathlessness index was 28. When they got the placebo, their breathlessness index was 32. And so on for subject 2, 3 and up to 12. So we're trying to here explain the role of randomization could play in carrying out the experiment. So we could use randomization to decide if the participant receives the drug or the placebo first. And again, this could have an impact because if they knew that they were getting the placebo, they might be like, I still can't breathe. Whereas if they knew they were getting the drug, they might psychologically think that they are breathing easier. So then, making no assumptions regarding the distribution of the data, investigate the claim at a 5% significance level that the drug significantly reduces the breathlessness index. Well, because we're not making any assumptions about the data, and it doesn't tell me here that there is any specific distribution of the data, then I am looking towards my distribution-free non-parametric tests. Now, remembering all the way back then, we have paired data, so that means that we're limited to the paired sign test and the paired Wilcoxon rank sign test. Remember, the paired Wilcoxon rank sign test does have an assumption that the distribution is symmetrical. So that means the only test that we have left is the paired sign test. So that means that my H0 is going to be that the median difference is 0. My H1 is going to be that the median difference, well, we're seeing if the drug significantly reduces the breathlessness. So if I'm going to do my subtraction as the drug minus the placebo, I want the drug to be smaller than the placebo. So if I'm doing drug minus placebo, I'm doing a small number, take away a bigger number, which means I'd be expecting it to be less than 0. So I'm wanting my median difference to be less than 0. So then I need to go through and do my subtractions and write down the sign that we end up with. So if I did 28 minus 32, I'd get a negative number. If I did 31 minus 33, I'd get a negative number. 17 minus 23, I'd get a negative number. 18 minus 26, I'd get a negative number. 31 minus 34, I'd get a negative number. 12 minus 17, I'd get a negative number. 33 minus 30, I'd get a positive number. 18 minus 19, I'd get a negative number. 25 minus 23, I'd get a positive number. 19 minus 21, I'd get a negative number. 17 minus 24, I'd get a negative number. And 16 minus 49, I'd get a negative number. So there we have 10 minuses. So the total of our minuses is 10. The total of our pluses is 2. So the total number of pieces of data that we're still looking at is 12. So then we have to use the binomial distribution. So X follows the binomial distribution with 12 as our number of trials. And because we're looking at the median, our probability is going to be 0.5. Remember to choose the smallest of your totals, which in this case is 2. And then we're looking at the probability that X is less than or equal to 2. And then we're going into dist, binomial, BCD. If you've got one of the new versions of the calculator, remember that your lower should be 0 and your upper should be whatever the biggest one is here, which is 2. Number of trials is 12 and the probability is 0.5. If you have one of the older versions of your calculator, you should just have X, N and P. And remember, it automatically does less than or equal to. So you just put in your 2 as your X, 12 as your N, and 0.5 as your P. And that ends up giving us 0.0193. This is our test statistic. Our critical value, well, it's a one-tailed test at a 5% significance level, so that gives us 0.05. So then as the test statistic is smaller than the critical value, we end up rejecting H0 at a 5% significance level. There is sufficient evidence to suggest the median breathlessness index is lower on the drug than the placebo. Now, if I was being asked how I would improve this experiment, I would actually have a look at the difference, because depending on the severity of the breathlessness that they originally experience, if they have a severe breathlessness attack or asthma attack or whatever it is that they're doing, then the severity of it initially will affect what their breathlessness index is an hour later. Whereas if it's only a mild breathlessness, then later on it's still likely that they would still have a lower breathlessness index. So that needs to really, in my eyes, be taken into account in this experiment. So I'd now like you just to take the time and think back over the last 2 years at all the different hypothesis tests that we have done, and write a list of when we have paired data, and write a list of where we have 2 groups of unpaired data. So hopefully you've taken the time to have a think about the hypothesis tests that we've looked at. There's actually only 3 for each of these categories. So we had a look at the paired sign test, the paired Wilcoxon rank sign test. Both of those were in AS, in the distribution-free non-parametric tests. And this year we had a look at the paired t-test. Now, for when we have 2 groups of data and it's unpaired data, we had the 2-sample t-test and the 2-sample z or normal test from this year. And we also had from last year, again in the distribution-free non-parametric section, we had the Wilcoxon rank sum test. And remember, for these tests where we have 2 groups of data and it's unpaired, those groups can be of different size. So always be careful when you are setting up an experiment. Just to add to this here, this does not include bivariate data. So if you wrote down anything to do with PMCC or SRCC, that's incorrect. We don't have 2 samples of data there. We have bivariate data. We have 2 different variables about the same subject, which is not having 2 samples. So as I was just saying, make sure when you're setting up an experiment that you're having a think. Have a think about what a placebo is. So remember, a placebo is usually a drug or an experience that means that it has no effect on the outcome really. Quite often they are saline, something like that, which would be used as given to a patient instead of an actual drug. And that would be given to the control group where you're not trying to see a change, and the experimental group has the effect, the treatment or whatever it is that you're actually experimenting with. So next time we are going to move on to having a look at analysis of variance, having a look at those types of analysis that we've talked about, the 1-factor analysis of variance and the 2-factor analysis of variance, which we use to analyse the randomised block design, the completely randomised design, and the randomised block design, respectively. And we're even going to have a look at the Latin square design. Thank you very much for listening.